Thank you. Okay, hi again. So in today's lecture, I believe this is lecture number 7, if I counted correctly. We're going to continue talking about graph algorithms. And in particular, we would start with more application of DFS. And we will show how to compute the strongly connected component of a directed graph. And then in the second part of the talk, we would start discussing shortest paths in a graph, and we will see the famous BFS algorithm. And if we'll have time, we'll start to see Dijkstra's algorithm, and probably we will not have time, but we will see Dijkstra algorithm either at the end of this talk or at the beginning of next week's talk. All right, so just to recall what we did last time, we talked about DFS, depth first search. It's sort of like a meta algorithm that we can change a little bit and get several beautiful algorithms. So we looked at the first version of this DFS where we just marked which vertices are visited. This was sort of like a silly algorithm because it's just you know, marked all vertices as visited by the end of the running time. But then we showed that, you know, you can adapt it slightly and get the connected components in an undirected graph. And this is already something interesting. It sort of tells us, you know, how you can partition a graph into, you know, islands where each island is connected and there are no edges between these islands. Then we talked about the, you know, the more difficult case, which is directed graphs. And we discussed pre and post numbers. I will recall what they mean in a few slides. But more or less it says, you know, the pre number is the first time in which a vertex was on the stack, and the post number is the last time where a vertex was on the stack. And we discuss, you know, which edges you're going to see in the DFS search tree. We talked about the tree edges. This is the edges that forms the tree or the forest. We talked about back edges, forward edges, and cross edges. And finally, we talked about directed acyclic graphs. These are graphs with no cycles. We proved and claimed that, you know, these graphs are exactly graphs where if you run DFS, you have no back edges. And then we showed that by the post numbers, if you sort the vertices according to descending post numbers, then you get a topological sort on a directed acyclic graph, meaning you are able to linearize the graph in a way that all edges go from left to right. So that's what we did last time. And today we're going to talk about, as I said, strongly connected component, BFS, and if we'll have time, Dijkstra's algorithm. All right. So by the way, let's do a quick poll. So how many of you seen Dijkstra's algorithm? So you can answer in the participants using yes or no. Okay, so I see most of you answer yes, a few said no. How many have seen the algorithm for strongly connected components? Let's clear first. Okay, how many of you seen the strongly connected components? Okay, so we'll have something new. And also, as I said, you know, we will revisit these algorithms that you are familiar with like DFS and BFS, but we will actually look at them from a more sophisticated point of view, and we will prove why they work. Okay, so maybe previously you programmed them, maybe you analyze the running time. Now we will actually prove in rigorous fashion why they work. Okay, so without much further ado, let's start. So I just want to, you know, I want to talk about strongly connected components. So I want to compare it to the simpler notion of connected components in undirected graphs. I'm recalling this picture of a maze that we saw in the previous talk. All right, and you write this graph. This is how the graph looks, and what are the connected components? Well, it's sort of very intuitive, right? So it's everything, like, let's say the connected component of A is everything that you can reach from A. So this is like one connected component, and the connected component of K is another one, right? And we saw how DFS can actually compute these connected components. So DFS would mark for everyone here, it will give a number 1. If we start, let's say, from A, and for everyone here, it will give the number 2. All right. So how do we tackle this question when we go up to directed graphs? Okay, so what about directed graphs? Yeah, by the way, so there's like a short way to write directed graphs. It sort of saves some time and space, so we call them digraphs. Okay, so from now on, I'm probably going to use this notation. Okay, so the first question is, what is even the right notion of connected components in directed graphs, right? So we will answer that. What's the right analog of connected components in the directed case? And the second is, how can we compute these components? How can an algorithm output these components? Okay, so we will do it in a very efficient manner, sort of as efficient as we were last time, where we run in time, which was linear in the size, linear in n plus m, which is just the size of the input. So it's linear in the input length. All right. So let's start. So connectivity in directed graphs, we say that two vertices u, v are strongly connected if there's a path from u to v and also a path from v to u. So I want to be able to go via directed edges from u to v and also to go via directed edges from v to u. So I gave this example, last time, for me to say that, my house is connected to Soda Hall, I really want to go from my house to Soda Hall and also back, right? I don't want to be stuck in one of these places forever. Okay. So this is the definition of relation. We say that two vertices satisfy this relation if there's a path from u to v and from v to u. So the first thing that we notice is that, this relation is an equivalence relation. So what does it mean? An equivalence relation satisfies three properties. So it should be reflexive, meaning that for every vertex, symmetric, meaning that if u and v are connected, then also v and u are connected. Sorry, are related. And the third thing is transitivity. We want that if u is connected to v, v is connected to w, then u is connected to w, right? And all these properties are very easy to check, right? So, right, there's a path from u to v and from v to u. Why is it transitive? Well, if there's a path from u to v and from v to w, then there's a path from u to w, and similarly, there's a path from w to u, because we assume that there's paths in both directions. Okay, so, this was a lot of words about just saying, this is an equivalence relation. What does it mean that we have an equivalence relation? It means that it partitions the vertices into equivalence classes. Okay, and in each equivalence class, everyone can reach everyone. There's a path from everyone in the equivalence class to everyone else. Okay, so this was, I think, probably a lot of words, but let's see an example just to make sure that we understand the concept. Okay, so let's look at this graph. So first, is this a directed acyclic graph in the example that you see here?
No.
No. Why?
There's a cycle between B and E.
Right, exactly. So there's a cycle between B and E. There are actually more than one cycle. We will soon see that there are several cycles. So what is connected to A? Let's start with A. Let's try to understand what is a strongly connected component of A. Which vertices are strongly connected to A?
No, none.
None, right? Because A doesn't have any incoming edge. So I cannot reach A unless I'm in A. So actually, yeah, so the strongly connected component of A is just A. What about B? Who is in the strongly connected component of B? E, right? Is it the only one? Yeah, so you can go from B to E and you can come back. But actually there's no other vertex that can go, that is strongly connected to B. What about D? D is isolated, right? You can reach D from other vertices, but you cannot reach from D to any other vertex. So D is not strongly connected to any other vertex. So D is on its own. C and F, similar to B and E, are strongly connected. And notice what's going on the bottom. On the bottom, actually, everyone is strongly connected to everyone else. So G, there's a cycle from G to H to K to L to J to I and back to G. So if you're somewhere along the cycle, you can get to anywhere else in the cycle, right? So this entire thing is strongly connected. Okay. All right, so we saw an example how you take a graph without any assumption. It's not a DAG, it's just a directed graph, and how we partitioned it into the strongly connected components. Now, notice what would happen if we shrink every strongly connected component to one vertex. Okay, so the question is of how do we do it actually? So let's say that we do it and we sort of have edges between these meta vertices. If there was an edge between one of the vertices in the two clouds. Okay, so that's what we're going to do next. And the question is, what will be the resulting new graph that we constructed out of this? Okay, so let's see. So again, what I'm doing, I'm taking the graph G, the graph on the left, and I'm shrinking every strongly connected component to it to a meta node. And I connect two meta nodes C and C prime that correspond to two components, if and only if there's an edge UV in the original graph, such that U is a vertex in the component C and V is a vertex in the component C prime. Okay, so for example, A and B are in different components, but there's an edge from A to B in the original graph. So there would be also an edge between the components of A and the component of B. Okay, so recall that, right? So these are the strongly connected components, right? And now I sort of shrunk every one of them to a meta node. And now I have a node A, B, E, C, F, D, and all the rest. And I sort of connect them if there's an edge. Right? By the way, if there are like 7 edges between two connected components, I'm just drawing one of them. Okay, so I'm not. For example, between BE and CF, there are 2 edges, but I'm just going to draw one. Okay, so is it clear what this operation is doing? Okay. So, and now let's look at this new graph. This graph, right? The graph on the right. the meta graph. What can you tell me about the structure of this graph? Right, I see some answers in the chat. So the structure on the right is a directed acyclic graph. Well, first it's a directed graph. Yeah, sure. But why is it acyclic? Why doesn't it have any cycles? Right? So let's assume by contradiction that there is a cycle. Let's say that you can go from here to here and then back. What would it tell us? It would tell us that you can actually go from any vertex here to any vertex here, and also from any vertex here you can go back to any vertex here. So actually BE and CF should also be in the same strongly connected component. So this would be a contradiction, therefore there's no cycles. Okay, so the claim is for every digraph G, when I build this metagraph, the strongly connected component metagraph, let's call it G prime, then G prime is always a directed acyclic graph. Okay, and sort of we gave the main reason. I mean, we need to, if you need to prove it rigorously, you need to write it down, but more or less we said the main reason why this is true. Okay, so it's kind of nice, right? Once we have this notion of strongly connected components, we see that every directed graph is a DAG on its strongly connected components. Okay, so it has sort of like, you can view it like you can zoom out. If you zoom out, you look at this metagraph. This metagraph is a DAG, and if you zoom in into one of these meta nodes, you see a component which is strongly connected, meaning that there's like paths from every two vertices inside every cloud or meta node. Okay, so it's a good time to stop for questions. So if you have questions now, this would be a good time. So we introduced a few definitions and we made a claim about this.
So if there's a graph that is named R prime, is it automatically the metagraph of G? Well, yeah, G prime.
Sorry, can you repeat? You said something about prime. I didn't understand.
Yeah, like the prime sign automatically means like the metagraph of something else.
I mean, it's just notation. I'm not sure that it's consistent with the book, so I'm sorry if it's not. I'm just saying, here I'm saying you take a graph G and you look at the strongly connected component metagraph G prime of G. Okay, so I'm saying this is always a DAG, all right?
I see, thanks.
I mean, yeah, so notation, we might change notation when we go along. So it's not like everything we always, like maybe sometimes you'll call G prime some other graph. So I don't want you to be fixed on this. Yeah, but what's more important is you understand the claim and what we were talking about. The notation is less important. Okay. Any more questions? You can either unmute yourself or raise your hand. I don't know. Okay, so it seems that things are clear so far, I hope. And let's continue. I now want to recall, from the previous lecture, the pre and post numbers in a DFS. Recall that the pre and post numbers in a DFS is, the pre number is the first time that the vertex was on the call stack of the DFS, and the post number is the last time that the vertex was on the stack. So here we see an example. We have a DFS where we start from A. So A, the pre number of A is 1. Then we go from A to B. The pre number of B is 2. Then we go from B to E. The pre number of E is 3, then we go to F and G, then we backtrack, then we go to H, then we backtrack more, then we go to C and D, and then we backtrack and finish the traversal. So here you can see marked all the pre and post numbers for every vertex. Okay, and it's a good exercise if you're still uncomfortable with this, this example, to try and do it on your own. You can also pick other orders. So maybe try to do the same example, but start from D instead of A. So it would give you a different tree. All right, so another way to look at pre and post numbers is that, what if we write the pre and post numbers on a line? So here you can see, right? So this is like at time 1, we are in the pre of A. In time 2, we are in the pre of B, and so on and so forth. And in time 16, we are in the post of A. So you can see that these are like sort of brackets, and these are legal brackets, meaning that I'm not, I'm not closing. Like what is an illegal sequence of brackets? Right, if I'm opening A, opening B, then closing A, and then closing B. Right, that's an illegal sequence of brackets. So here it will be a legal sequence of brackets, and this is what we discussed last time. And if you look at any two vertices that are connected by an edge, we discuss, what are the possible relations between the brackets of these two vertices. So let's say U and V. So, and we said that, U and V is a back edge. Let's say if the order is like V, U, U, V. Okay, and you can see it in this example. For example, what is a back edge here? So this, for example, the one from F to B is a back edge. And indeed, FB is a back edge. Indeed, the interval of F is contained in the interval of B. Okay. We also discussed cross edges, like this one, D to H. The cross edge from D to H. So how does it look? It looks like this. You have H, and then you have D. And so the intervals are disjoint, and H finishes before D starts. And the edge is between D to H. And we call this a cross edge. So all these, all these types of edges can be figured out from the, pre and post numbers. Okay, and we talked about how you can use the post numbers if the graph was a DAG. If the graph was a DAG, well, we've said a few things. So if the graph is a DAG, this happens actually if and only if there are no back edges. If there's a back edge, it indicates that there's a cycle, and actually that's, if there's a cycle, we would also always find the back edge. Okay, and if there are no back edges, then the post numbers, if we sort the vertices according to their post numbers, this gives us a topological sort. It gives us a way to linearize the graph such that all the edges go from left to right. Okay, so I see that Alice raised her hand. Alice, do you want to ask the question?
Would it make sense if there's, or can we not do a cross edge from H to D?
The cross edge is from D to H. If there was an edge from H to D, then this would not be the structure of the tree, right? Because when we go to H, when we develop H, we would see that D is actually reachable, but was not visited before. So we would have D here below. So therefore, no, we cannot have a cross edge in the opposite direction.
Okay, thank you.
Okay, so I can see why all these things are a little bit confusing, but there are only like 3 options. So just work out like 1 or 2 examples, and you would figure it out. I think it's confusing because, you know, when you have only two possibilities for things, it's very confusing, at least to me. Like if like the answer could be plus or minus, I always get it wrong. Okay, or left or right. Okay. So, right, sorry. All right, so let's go back to maybe this example. So let's say that we want to find the strongly connected components, right? So it would be very nice if we can start a DFS from this node, right? If we start a DFS from the node H, then what will be revealed during the DFS from H?
We get stuck in the cycle.
We get stuck on a cycle, but what cycle? Which cycle? The cycle GHIJLK. So actually, this is a good scenario for us. So if we start a DFS from H, we will find the entire strongly connected component of H, and nothing more than that, because H is in a sink in the metagraph, right? So we cannot reach any other meta node, but we will reach everything, every node inside the strongly connected component of H. So if we run DFS from H, we figure out the strongly connected component of H. Now, right? So, but notice that right? This is what we want to compute, right? So we don't have it in our hand, the thing on the right. What we have is the thing on the left. So how can we find? Okay, let's ask another question. What will happen if we run DFS from A, let's say? Then we'll just, you know, reveal everything in the graph. So when we do DFS from A, what we reveal is not inside the same strongly connected component, right? It's everything. So actually, a DFS from A is not so good for us. A DFS from H is very good for us. So how can we find a vertex that for sure is in one of the sinks of the metagraph? If we can find it, then that would be great, because we can sort of figure out that this is a strongly connected component, remove it from the graph, and then continue recursively. Okay, so the question is how to find a vertex in you know, one of the sinks of the metagraph. Okay, I actually don't know how to answer this question. So let me ask you a different question. I mean, maybe you'll find an answer, but I don't know how to solve that. I'm changing the question a bit. How can you find a vertex which is in one of the source strongly connected components? Okay, so in particular here, we will look for the vertex A. How can we find the vertex A? Okay, so and recall what we know about, you know, post numbers. We said that, you know, if the graph was a DAG, then the vertex with the biggest post number would be the first in topological order, you know, when we linearize the graph. So it will be in fact a source. And it turns out that this works also in graphs that are not DAGs. Okay, so the claim is that if you run DFS on G, okay, the original graph, and you take the node with highest post number, then this node is in a source strongly connected component. Okay. Now, before we prove this claim, and I mean, proving this claim would take us the entire slide. So I mean, it's not a trivial claim, but it's also not too hard. But why is it useful? I mean, we wanted a sink, not a source. So how can a source help us? Any ideas? Okay. Yeah. So great. I see great comments in the chat. So what would happen if we sort of look at the graph G and just flip the direction of all the edges? We take the reverse of the graph, right? Okay, it's really a long example, so maybe we'll not do it, but you know, let's say I'm like replacing all the directions, right? So what would happen is that the strongly connected components are still the same, right? So if there's a path from U to V and from V to U, and now I'm reversing all directions, there's also a path from U to V and from V to U. So the structure of the components would be the same, but the edges between components will be reversed. So that's if I'm looking at the reversed graph. The reverse graph, let's say prime, and the reverse graph. Okay, so if we can find a source in the reverse graph, or actually a strongly connected component source in the reverse graph, then we found a strongly connected component sink in the original graph, right? So here to find a source is really to find either this guy or this guy, and both of them are sinks in the original graph, in the original G prime, right? Okay, so that will be the plan, and now we need to prove that indeed this works, right? So that picking the one with the biggest post number gives us a source strongly connected component. Okay, so how are we going to prove it? Well, we said that in graphs it's very useful to prove things by contradiction, and also here this would be the approach. So let's assume that this is not the case. So okay, so let's denote by V. Let V be the node with highest post number. Denote by C, it will be the strongly connected component of V. And we sort of assume that C is not a source. So what does it mean? It means that there exists another component, C prime, such that C prime has an edge to C in the meta graph, right? I mean, if there's no such C prime, then C is a source and we're done, right? So let's assume that C is not a source. There must be another component, C prime. Okay, so let's look at the picture. We have G, this cloud of vertices. We have V somewhere here. V is surrounded by its connected component C. And we have another strongly connected component, C prime. And we know that there must be an edge from C prime to C. C is the strongly connected component of V. It's the strongly connected component of a vertex is uniquely defined, right? It's just every vertex for which we can reach from V to this vertex and go back also. So C is well defined based on V. All right. So I want to show that this cannot happen. How will I show it? I will show that actually there must be someone in C prime that has a larger post number than V. And this will be a contradiction because we assume that V is the one with highest post number. Okay, so I want you to consider the first vertex U in, the union of these two connected components that we explore, that is explored by DFS. Okay, we explore DFS. Eventually, we would explore all the vertices. We look at all vertices in C and C prime, and we look at which one was the one that we explored first. Okay, so there are two cases. What happens if U is in C? Right, in particular, it could be V. What would happen? We start exploring, at some point in our exploration, we reach U. When we reached U, we haven't explored any other vertex in C and any other vertex in C prime. So what would happen? When we do the explore on starting from U, we would reveal everything that you can reach from U. Right? This is the property of DFS. When you start explore from a vertex, you reach every possible vertex that you can reach from U. In particular, you would reach all the connected components C. In particular, you would reach V, and you would also not reach any of the vertices in C prime, right? So sort of like when you run the DFS from U, you would reveal all of C, but you cannot reach C prime because there's no edge going from C to C prime, and there's no path going from C to C prime. So in this case, we would process all the vertices in C, okay? And then we're gonna backtrack, and we're gonna, pop them from the stack. And only after, when we continue DFS from maybe another node, we would start exploring C prime. So meaning, we would sort of reveal all these nodes in C, and then we would, backtrack. So we will pop all these elements from the stack. And then maybe we would start exploring again, maybe from another node, and eventually we'd reach C prime, and then we would explore all of C prime. So in this case, all the post numbers in C would be would be smaller than all the post numbers in C prime, because we would finish process C before we started processing C prime. So this would be a contradiction because we assume that the biggest post number is in C. That would reach a contradiction to the maximality of V. What's the other case? The other case is where this first vertex U was in C prime. Okay, so let's look at it again. Sorry about the mess here. So recall we have this C, C prime, we have V, now we have U. So U is the first vertex in both the component of C and C prime that we visit. What would happen when we visit U? We would explore everything that is reachable from U, right? And we have to explore all of that before we pop U from the stack. So when we start the exploration from U, we would reveal C prime, C, and eventually, after finishing all, processing all these vertices, we would pop U from the stack. So here, we would have that post U is bigger than post V, because at some point we would reach V, process it, pop it from the stack, but we still haven't finished processing U, and eventually we would pop U from the stack. So U would have a higher post number. In both cases, we got a contradiction. And this proved, what did we prove? We proved that if we take the vertex with the highest post number, then this vertex belongs to a source strongly connected component. Okay. All right, so I think this was like the hardest proof that we saw so far. So it would be a great time for questions.
Could you please go over the C prime case again?
Right. So what would happen if the first vertex that we explored in C union C prime was a vertex U that belongs to C prime? What happens when we run explore from U? We reveal all the nodes in C prime because they are reachable from U, and also all nodes in C because they are also reachable from U, right? And once we process all of them, only after we process all of them, we're gonna post-process U, and the post number of U would be the highest among all C and C prime. In particular, it will be higher than the post number of V, and this is a contradiction.
Thank you.
Okay. So I claim that actually we proved something stronger than that, and we will need it for the algorithm. Not only did we show that the vertex with the highest post number is in a source, we also show that if we look at two connected components, C and C prime, and we have an edge from C prime to C, then the highest post number in C prime is bigger than the highest post number in C. That's actually, that's actually what we proved if you think about it, right? So whenever we have two, sorry. Let's just do it. So what we actually proved is that, if you rerun DFS on G, then for every two strongly connected components, C prime, that has an edge to C, the highest post number in C prime is bigger than the highest post number in C. And this is also should look familiar. What happens in a DAG? In a DAG, the strongly connected components are just single vertices. And then, if we have an edge, we know that the post number in the beginning of the edge is higher than the post number in the, in the other side of the edge. So it's sort of like what we saw earlier about post numbers in DAGs is sort of a special case of this claim. All right. So, and the proof is just the same proof. So now that we have this thing, how do we figure out the strongly connected components? Right. So this will be a slight adaptation of DFS. We're going to first run DFS on the reverse graph. Okay, so we're going to reverse all the directions of the edges. We're going to run DFS on this reverse graph, and we're going to get post numbers from this DFS. Okay? And now I'm forgetting whatever DFS was doing. I'm only remembering the post numbers that the DFS gave me. And now I'm starting sort of another DFS, but I'm going to tweak it a little bit. So I'm going to initialize things. So first I'm going to, put a flag for every vertex, whether I visited this vertex or not. I'm initializing it to false. And I also write for every vertex what what is the strongly connected component number that it belongs to. So in the end, I want to sort of give numbers to vertices such that two vertices are in the same strongly connected components if they have the same number. Okay, so this is sort of very similar to what we have in the connected components. So the main, the delicate, important detail is that we are not doing DFS in an arbitrary order, but we're gonna do the DFS order. Okay, so that's maybe the most crucial thing, ordered by the post number on the reverse graph. And by order, I mean that we start with the one with highest. Okay, so this is in descending order. Right, so we start by exploring from V, which has the highest post number in the reverse graph. Okay, what do we know about this vertex? We know that it belongs to a source in G reverse, or in other words, it belongs to a sink in G, right? And then we start exploring from this vertex. We finish exploring for this vertex. What have we revealed? The strongly connected component of V, right? Why? Because V is in a sink, right? This was the claim that we proved. Now we continue to the next one, the next vertex that we have not considered so far and has the highest post number according to G reverse. It must be again a sink in the remaining graph. Maybe, so maybe let's say, okay, so here we had like this graph, GH. Right, so what did we have? We have this graph A, B, E.
Professor, the Tools tab is blocking the bottom of the screen.
Okay. Sorry. Yeah, maybe I should avoid writing at the bottom of the screen. Right, so I guess maybe I'm mistaking the names of the vertices. This is the graph that we had. So we start by picking the one with the highest post number. Maybe we're picking this, like a vertex from here. We explore this entire connected component. We reveal this strongly connected component. Now we pick the next one with highest post number according to the reverse graph. This will be maybe this guy. We reveal it, and so on and so forth. So every time we reveal, we sort of like, erase parts of the graph, and then we continue on the remaining parts. Right, and explore is again, as we had in DFS, we just mark vertices that we visited, and we mark the strongly connected component of every vertex. Okay, so notice that, over the past lecture and a half, we looked at a very simple algorithm, DFS, but we saw that by tweaking it and adding like pre-number, post numbers, and adding some, maybe global counters, we can actually compute very sophisticated things. We can compute the connected components, we can compute the topological sort if we are in the DAG, and we can compute the strongly connected components. And this required slightly more sophistication because we needed to run DFS twice, once to get the post numbers, and then to use these post numbers to give the right order for us to explore the graph. And when we are exploring the graph in the right order, we are revealing the strongly connected components. Okay, so any question so far? This sort of finishes the first part of the talk, and then next we're going to move to something completely different. So this is a great place to ask for questions.
I have one question. So when you run DFS on the reverse of the graph, you can start at any arbitrary point. Is that correct?
Yes. Yeah, so the DFS on the reverse, I don't care about the order. Any order would work, right? We proved that that when we do the DFS on the reverse graph, sort of like the vertex with the highest post number would be in a source of the reverse graph, or equivalently in a sink of the original graph. And this was regardless of the order, right?
Rishab asks, why do we need to reverse the graph? Why can't we just repeatedly remove sources from the original graph?
Okay, so the point is that let's say that we figure out, that A is a source. It's not clear how we find, that A is in a source strongly connected component. It's not clear how this helps us, right? If we start DFS from A, we would find out many vertices that many of them are not in, all of them except for A are not in the strongly connected component from A. So starting DFS from a source does not reveal the strongly connected component of A, it reveals many more vertices. Whereas if you start a DFS from somewhere here, where you had this cycle, then all you're gonna see, all you're gonna reveal or visit is just this cycle. So you would actually figure out that the strongly connected component starting from this vertex is actually this cycle. And that's the point. Now, there are actually several variants. So it's not the only way to compute the strongly connected component. There are actually algorithms that even predate this algorithm. I forget who came up with this very brilliant algorithm. Maybe someone would write it in the chat. So there are other algorithms that are more complicated, and they are only running DFS once. So they are remembering a little bit more information, and somehow they are able to compute the strongly connected components. If you are really interested in that, maybe you should look it up. This one, I think, is the most elegant one, but it's quite tricky because it's sort of like you have to do it in the right order. If you are not doing it in the right order, it will not work. So, okay, so did anyone figure out who is the author of this algorithm? Okay, if not, I will mention it next time. All right, so I guess I want to move now to a new topic. So this new topic, you probably are familiar with it because you already mentioned that you know DFS and you know Dijkstra, but we're gonna look at it again, and hopefully we'll learn many new things. In particular, we would prove why these algorithms work. And we would also look at more challenging scenarios where we have maybe negative edges, and we see how to handle this case. Okay, so graphs represent many things, and one famous example that we gave in the first talk about graph is that they can represent roads, right? So it's very natural to ask, given a graph, what is the distance between two cities, right? So let's start by thinking of all the roads as having equal distance. So let's say distance 1. Okay. What are the distances? What is the distance between A and let's say B? Well, A and B are neighbors, and so therefore the distance between them is 1. What is the distance between A and C? Well, you need to make, you need to go over 2 edges in order to get from A to C. So the distance is 2, and you cannot do it in less than 2. So let's just answer very quickly. What are the distances from A to all other vertices? So the distance from A to A, what is it? It's 0. You don't need to take any edge. From A to B, it's 1. A to D is 1. A to C is 2. And A to E is right? And sometimes we have several paths with the same length. So for example, between A and C, we have 2 paths of length 2, right? And there's also like longer paths. So we can also go from A to C. We can go A, B, D, C, which is longer than 2, but that's not the shortest path. So we are interested in the shortest path, right? Okay, so the natural question is, how can you? So let's assume that all these, all these distances are 1. How can you compute the distance between A and, let's say, all other vertices? So there's a very when I looked at it in the book, it's the first time that I heard this explanation. I think it's a very beautiful explanation. So one thing that you can imagine is that you have maybe small marbles representing every vertex. You have very, very thin strings connecting every 2 vertices, and the thin strings are, let's say, 1 foot long, each of them. And then you sort of pick A, and you look what happens to all the other marbles. So what you'll see is that you'll have A on top, right? And then you'll have B and D. And then you'll have C and also E. So B and D are of distance 1 from A. C and E are of distance 2 from A. And this is like a physical algorithm. You didn't need a computer to compute it. You just need, to implement it physically and, take A and then measure. I think it's very nice. I haven't seen this example before. So let's take this. I don't know. I think it's very inspiring. But let's think for a second. How can we figure out the distances from A? Right. So we have this. Let's say we have a very big graph, and we start from A. So which are the vertices that are of distance 0 from A? Well, it's just A. Right? A is the only one of distance 0. Which are the vertices of distance 1 from A? Okay, so maybe you have a good answer for that. Right, it's just all the neighbors of A. Okay, so now it's like, these are all the neighbors. They would be of distance 1. Who will be the vertices of distance 2 from A? Well, it's like in Facebook, right? It's the friends of your friends. But usually when you think of someone who is a friend of a friend, you would not call your friend a friend of a friend, right? Because it's also your friend. So it's anyone that is not already discovered, but who is a friend of the friend. Okay, so it's a neighbor of a neighbor that is not a neighbor, or also not A itself. Like I would not call myself a friend of myself. So it's everything that was not revealed previously that is a neighbor of the neighbors. It's a neighbors of neighbors. But not revealed before. Okay, so this gives us a very simple algorithm. I mean, sort of this procedure that I described actually gives the algorithm. So let's see how the algorithm looks like. So I want to compute all the distances from a starting vertex S. So I have an array of distances, and I start the distance of S to itself. This will be 0. And for every other vertex, I initialize the distance to be, I mean, I could initialize it in various ways, but it's very convenient to initialize it to infinity, because then I don't need to worry about, whether or not this variable is initialized or not. Okay, and right, so this is for every vertex that is different than S. right, so I'm going to present it a little bit differently than in the book, but it's equivalent, and I think it's easier to see why it works. So I want to sort of simulate the algorithm that we saw in this picture. So I want to start with, I want to write the layers in this graph. So the first layer would be just the vertex S. The second layer would be just the neighbors of S, and so on and so forth. So the first layer would be just S. And now I want to compute from the, from the current layer, I want to compute the next layer. So, okay, so while the current layer is not the empty set, sorry, the empty list, I'm going to initialize the next layer to be the empty list. And I'm going to, put everyone that is supposed to be there, I'm going to put there. So I'm going to iterate over all vertices in the current layer. And I'm going to go over all edges between a vertex V and another vertex U. And I'm going to check. If U was discovered already, then the distance would have been smaller than infinity. So I'm checking whether the distance is infinity. If the distance is infinity, it means that we sort of haven't found a way to reach U yet. So if this is the case, then we update the distance to U to be the distance to V plus 1. And we append U to the next layer. Okay. And once we finish iterating over the entire layer, we figure out all the neighbors of the current layer that was not revealed before. And now we can continue by, in the next iteration of the while loop, the current layer would be just the next layer. Yeah. Okay. So this is sort of like writing in pseudocode the algorithms that we saw earlier. And we can prove that this algorithm indeed computes the distances. So in order to do that, it's important to have the right claim. So the right claim is as follows. So in iteration I of the while loop, we identify all vertices of distance exactly I from S. Okay, so that's the claim. And the way you prove it is by induction on I. So I will not go into the details, but it's not that complicated, right? So in the first layer, what you're gonna identify is all the neighbors of S. So these are indeed the ones that are of distance 1 from S. And so this is a base case, and all the other cases are simple induction, right? So we assume that we revealed everything of distance up to I, and now we need to reveal everything of distance I plus 1. It must be, in order to be of distance I plus 1, I have to have someone of distance I such that I have an edge from this vertex to me. So therefore I would be identified also everything that I identify as a path of distance I plus 1. So, okay, so I'm not going to go into the details of this, but you can try to do it as an exercise. I want to say maybe what is the difference between this and the book. So actually, if you think about it, what would happen? So let's look at the graph we had before. And let's say that this is a graph. Let's say that this is a graph. So what would happen? In the first iteration, the current layer would be A. Then we would process A, and we would add all the neighbors of A to the list. So then this would be our list. And then in the end, we would process B, doesn't have any new neighbors. C has E, and D has no new neighbors. So then the next layer would be E. But notice that we didn't really need to consider this current layer and next layer. We didn't really need to have two, I don't know, lists or arrays. We could just treat it as one list and append the vertex that we reveal to the end of this list and pop from the beginning of this list. So we didn't need these two variables, current layer and next layer. We could have used only one of them. So we can do it with a queue while the queue is non-empty. Right, so now we don't need to iterate. So now we just take V to be the first element in the queue. And here we add to the queue we inject to the queue U. And then we don't need to. If you think about it, this is giving you the exact same thing. It's sort of like instead of having these two arrays in separate places, you just have them one next to the other, and sort of the dividing line between them is sort of blurred out. You don't really see it, but it's not important to see it. Still, I think that the version with the layers is easier to prove that it works. So in the version with the queues, it's a little bit more complicated because you have these intermediate steps where you have several neighbors in the queue and several neighbors of neighbors in the queue. Okay, so any questions about BFS? About the algorithm. And the next thing that we're going to do is we're going to analyze the running time, which is not going to be too complicated. Yes, so I don't know if I want to say push and pop because this is a queue. So a queue is the first in, first out. And a stack is a last in, first out. And if you think about it, that's the main difference between BFS and DFS. So in both algorithms, you're sort of, every time we're like picking a vertex and we are looking at all its neighbors. But the question is which vertex to pick. In DFS, we're always picking the one that is deepest in our search tree. And in BFS, we're always picking the one that is shallowest in the search tree. And this is sort of realized by the difference between queue and a stack. You can also, there are also algorithms that use heuristics, for example, A star, and then you're sort of developing in each iteration the vertex for which the distance plus some heuristic function is the smallest. And this works well in practice. At least it was a very popular algorithm, several years ago, but I'm not sure if it's used that much now. All right. So next, what is the running time of BFS? Well, this is very similar to DFS. How did we argue about DFS? we just, you know, looked at how many times we process a vertex and how many times we process an edge, right? So also here in BFS, every vertex is inserted to the queue most once, and ejected from the queue at most once. So we will never put the same vertex in the queue twice. Why? Because once we put him in the queue, we set the distance of this vertex, and the only way that we can insert a vertex to the queue is if the distance was infinity. So we can never insert a vertex more than once, and every edge is considered, you know, how many times? Well, it depends. If the graph is directed, then at most once. If it's a digraph, or at most twice if it's a undirected graph. Anyway, it's order 1, right? So the total amount of operation we do is order n plus m, where I remind you that n is the number of vertices and m is the number of edges. Right, so this is again a linear time algorithm that computes all the distances. Notice that, you know, this is another algorithm that allows us to explore a graph, right? So in particular, we could have computed, based on BFS, we could have computed connected components if we wanted. All right, in undirected graphs. Okay, so any questions about that? BFS is a fairly simple algorithm. Notice that in DFS, we sort of, like once we explored everything that we can reach from S, we restarted it, you know, if we haven't visited something else, maybe it was not in the connected component of S, we restarted. In BFS, we are really interested in the distances from S. So, you know, everything that is not in the connected component of S, we just ignore it, right? So if we have like here S connected to a bunch of vertices, and I don't know, we have T here, you know, we run BFS from S, we revealed A, B, and C. We haven't revealed T because there is no path from S to T. Okay. All right. So this was a simple algorithm, but it sort of had a slightly unnatural assumption. The assumption was that the weights or the distances on edges are all one, are all the same. So in particular, if you think of roads, it's not a natural assumption, right? Like every road has a different length. So next we want to talk about shortest path when we have weights on edges. So we have a graph composed of vertices and edges. And in addition, we have a length function that gives for every edge in E, it gives a length, which is a number. We'll start with talking about non-negative numbers, or actually positive numbers. And for simplicity, let's assume that there are also integers. I mean, what we're going to say would work just as well if these are real numbers. But, you know, just for simplicity, let's assume that these are integers, so that we would not need to talk about precision issues. All right, so let's see an example. So let's say we have A, B, and C, because it's a very simple example. And the distance here is 100, here it's 50, and here it's 200. So what's the distance between A and B? It's 100, right? there are two ways to go from A to B, one direct and the other crossing through C, but the direct one is better. What about from A to C? Well, going directly from A to C is not the right one, the shortest path. The shortest path is actually going through B, and this would cost you 150. So, okay, so we sort of understand how to solve it on small graphs, but how can we solve it algorithmically when the graph size grows? So one approach is, and this is something that you should think about as a very useful tip. Whenever we ask you to solve something that is new and that you haven't seen yet, it's always a good idea to think if you can use the tools that you already know in order to solve it. Meaning, can you apply some reduction from the questions that you are trying to solve to a question that you already know how to solve? So how can we apply some reduction, some transformation on the input so that we know how to solve the question? So the idea is that we can just replace every edge with a lot of small edges. So we just take, okay, so the edge from A to B is of length 100. So what would happen if I add like 99 intermediate stop points? And so 99 intermediate points, intermediate vertices. And now the distance between A and B, even if I'm thinking of all these as distance one, is, the distance of this meta edge is like the distance of the original edge in the graph. And I can do the same thing between A and C, and B and C. So here I would have 49 intermediate. And here we would have 199 intermediates. And now I'm looking, I started from this graph G and I got this graph G tilde. And I'm now going to compute BFS on G tilde. In G tilde, all the distances are 1. And if I compute, BFS on G tilde, then I know what is the distance between A and B and what is the distance between A and C, right? So this is an algorithm that works. It actually produces the distances between A and B and A and C. What's the problem with this algorithm? Why aren't we satisfied with it? Well, if you notice, we started with a very small input. We sort of had only 3 numbers that each one of them could represent as 8 bits. And we grew to a very large graph with, I don't know, almost 400 vertices. So, and if you take it to the extreme, then, these numbers could be n bits. And then this path would be, of length 2 to the n. So this is not an polynomial time algorithm. This algorithm may take exponential time in the bit complexity of the weights. If the weights are 2 to the n, which can be represented by n bits, then the algorithm would take time roughly 2 to the n. So this is an exponential time algorithm. And we don't really consider these algorithms as efficient, right? So we are here talking about, in this class, we are describing algorithms that are efficient. Most of them are in polynomial time. In fact, most of them are in linear time or almost linear time. So this is not an algorithm that we would be satisfied with. Later in the class, we will see that for some problems, we don't have better than exponential time algorithms. And this would sort of in our mind would mean that these problems are intractable, or more precisely that the best algorithms that we know for certain problems are exponential. And these are what's called NP-complete problems. But this would be, in the last part of the semester. Okay, so this sort of works, but is not efficient. Next time we're gonna see Dijkstra's algorithm, which sort of, if you think about it, I mean, one way to think about it is that you sort of look at this reduction and you notice that this reduction is not very efficient in some sense. Where we run BFS from A, it's sort of very predictable. We know that for 100 steps, nothing would happen. We would not reach before we reach B. So the Dijkstra's algorithm can be seen as a way to sort of run this very slow algorithm much, much faster. We would prove that the Dijkstra's algorithm is correct, that it does produce the right distances. Correct. We would analyze its runtime, and this would depend a little bit on the data structures that we are going to use. So there will be some intersection with data structures, but we will not go in much details into data structures. And then we're going to discuss what to do with negative weights. Okay, so even if you think about it, this reduction worked because all the weights were integers and positive. It's not clear what would happen if between A and B the distance was -100. I mean, we need to figure out how to solve the problem in this case. Okay, so that will be next Tuesday. Yeah, so it will be a good time to stop now and to, if you have any more questions, I will be able to answer. I see that we're running a little bit behind schedule, so feel free to leave if you need. Yeah. Okay, so I'm gonna stay here for a few minutes to answer your questions, and